Welcome to Lesson 17, Solving a Spring Problem with a Periodic External Force. In the problem that we'll look at, we have a mass attached to a spring, which is attached to a wall. We have a number line to keep track of where this mass is, and we'll let x of t be the position of this mass, let's say where it's hooked to the spring here, at time t. We'll assume that 0 is the equilibrium position for this mass and spring system. This mass will move in some way, and it will experience a restoring force due to the spring, capital F sub s, by Hooke's law. We also could have a drag force. Maybe there's a fluid encompassing this whole thing, and there's a frictional drag force due to the fluid. We have a velocity at some time t. It varies with t most likely. And we have an external force F of t. Maybe we have a rocket engine attached to this mass in some way to provide an external force. In the problem that we're going to look at, this force F of t will be periodic with period 2. We can handle periods of other sizes also. But we'll look at this type of function to begin with. The goals of the lesson are to be able to write a periodic function in terms of unit step functions. We'll see how to do that. We'll learn how to find a formula for the Laplace transform of a general periodic function. If we know the formula for the periodic function over one period, we can write down a formula for the Laplace transform of that periodic function. We'll use this representation, Laplace transform, to solve an initial value problem with a non-homogeneous term on the right-hand side, which is periodic. And we'll solve a mass and spring problem. And once we have the solution, we'll look at it to see if it seems reasonable. We will also, at this time, generalize the formula for the Laplace transform of any periodic function, not just the one of period 2 that we're going to first look at. So here's the problem. This is the spring and mass system. A wall over here, the spring stretched or compressed perhaps, a mass m here. There's a restoring force due to the spring given by Hooke's law. We have a force due to frictional drag. This mass and spring might be going through a fluid, and that would involve then some drag. We'll let v be the velocity of this mass. V depends on time t. We'll let f of t be a periodic force function, external force function applied to this mass. We'll first look at a force function f of t whose graph looks like this. Between t equals 0 and 2, it's a straight line starting at the origin and going up to 2 on the vertical axis. Then our function, so this part of the graph is just f of t equals t, which is what we have right here. We're going to assume that this function is periodic with period 2. So between 2 and 4, this function's graph will look like it does over here. Between 4 and 6, this part of the graph will also look as it does over here, and so on. Keeps going on towards infinity periodically. We're going to consider this differential equation for this spring system. The second derivative of x with respect to t plus 10x prime of t plus 24x of t equals f of t. X of t is the position of this mass at any time t. And we'll look at fairly simple initial conditions. At time 0, the position of the mass starts at 0 over here, and it also has an initial velocity of 0. So let's suppose that this is our periodic function f of t. Our goal is to find a formula for the Laplace transform of f of t, capital F of s. So here's how we're going to do it. We're going to look at this function f of t. From that, we're going to subtract the function u of t minus 2, f of t minus 2. Here the period is 2. So we just shift it over 2 units. This moves over to here, this one moves over to here, and so forth. Now if we subtract them, this part of this function subtracts off this part of this function, leaving only this part remaining. The rest will be 0. So when we take this graph minus this graph, or perhaps I should say this function minus this function, what's left is a function that looks like this. Between 0 and 2, it's just the function f of t minus u of t minus 2, f of t minus 2. This subtracting this gives us this part, which is primarily maybe non-zero, and the rest of the way out here it's just 0. Okay? So in that case, if I want to find the Laplace transform of this function using our formula, well, what would it be? The Laplace transform of this function would be the integral from 0 to infinity e to the minus st f of t dt. But for t between 2 and infinity, this function is just 0. Integrating 0 gives us 0. So this Laplace transform just simplifies to the integral from 0 to 2 of e to the minus st f of t dt. Now in this particular example, f of t is t, and so we then get the integral from 0 to 2 t e to the minus st dt. Just remembering that this f of t in this example is t. This is an easy integral to evaluate. I'll leave it to you. We'll see the results soon. It can be integrated by parts. If you let u be t and let dv be e to the minus st dt, and then use the formula that it's going to be u times v minus the integral of v du, the integration by parts formula. You should try it. It's not hard. So let's look at this example. Suppose that we have this function once again. F of t is t if t is between 0 and 2. That gives us part of the graph right here. And we're also told that t is periodic with period equal to 2. And that tells us what the rest of the graph out here looks like. And so for this function, f of t, we want to find the Laplace transform capital F of s. Okay, well, on the last slide, we saw that the Laplace transform of f of t minus u of t minus 2, f of t minus 2, was just the integral from 0 to 2 e to the minus st f of t dt. This held because f was periodic with period equal to 2. So, if we look at this left-hand side, the Laplace transform of f of t is capital F of s, minus the Laplace transform of u of t minus 2, f of t minus 2. By our properties of Laplace transforms, we know that the Laplace transform of this is e to the minus 2s capital F of s. And on the right-hand side, we have the integral representation of the Laplace transform of this side, realizing that the integrand was only non-zero between 0 and 2. And so we now have this formula. Going from this second equation down to the third, we just recognize that capital F of s is in both terms of this left-hand side. so factor it out. The quantity 1 minus e to the minus 2s times f of s is the integral from 0 to 2 e to the minus st f of t dt. Okay, so at this stage, if we divide by this factor 1 minus e to the minus 2s, we can solve for capital F of s, the Laplace transform of this function over here, this periodic function. So capital F of s is 1 over 1 minus e to the minus 2s times the integral from 0 to 2 e to the minus s f of t dt. Now, between 0 and 2, f of t is just t. So this integral plus this factor out front is 1 over 1 minus e to the minus 2s, integral from 0 to 2, t times e to the minus st dt. Just use the fact that between 0 and 2, f of t was equal to t. Now, if we look at this integral, as I mentioned earlier, we can evaluate this using integration by parts. When you do, you'll get this expression down here. This first factor is just the one that's in front of the integral, and when we evaluate this integral from 0 to 2 of this stuff, we'll find out that it's equal to minus this fraction, the quantity 2s plus 1 times e to the minus 2s divided by s squared, plus the fraction 1 over s squared. So we have two factors in this formula for f of s. This fraction times all of this stuff. Now, there is nothing particular about using a function periodic with period 2. We could have used the same technique to find the Laplace transform of any function that has a period of p. P might be 2, might be some other number. So we have the following fact. If a function f of t is defined on 0 to infinity and has period p, then its Laplace transform is 1 over 1 minus e to the ps power times the integral from 0 to p e to the minus st times f of t dt. Notice in this integral we're integrating with respect to t, and so its value is going to depend on s. We can think of this integral right here as being some function that depends on the value s multiplied by this, which also depends on s. So this formula does make sense. It does give us the Laplace transform being a function of s as we would expect it to be. So let's consider the following problem. We have an initial value problem here. Solve x double prime of t plus 10x prime of t plus 24 times x of t equals f of t, where f of t is equal to t for t between 0 and 2, and f of t is periodic with period equal to 2. So let's look at the graph down here. Between 0 and 2, the graph looks like f of t equals t. So it starts at the origin 0, 0, and it ends up here at 2, 2. Then the second part tells us that f is periodic with period 2. So between 2 and 4, the graph looks exactly like it did between 0 and 2. And then it repeats itself over and over and over ad infinitum. So, x of 0, our initial position, if we're thinking of this as a mass attached to a spring problem, the initial position of the mass is 0. The initial displacement is 0. We're measuring position from the equilibrium point of displacement. And the velocity, x prime of 0, is also 0. So let's start with this differential equation, which we have down here. Let's take the Laplace transform of both sides. So the Laplace transform of this left-hand side equals the Laplace transform of the right-hand side. This f of t we looked at just a little while ago on a previous slide, and we found out that its Laplace transform was this stuff right here. Okay, now let's see. Let's look at the left-hand side a little bit further. The Laplace transform of x double prime of t is going to be s squared times capital X of s. Those terms that have little x of 0 and little x prime of 0 in them are both 0 because of these initial conditions. Similarly, the Laplace transform of 10 little x prime of t is just 10 times s times capital X of s. The Laplace transform of 24 little x of t is 24 times capital X of s, and the right-hand side I'll leave unchanged. Okay, now we notice that on the left-hand side, coming down to here basically, every term on the left-hand side has a factor of x sub s. So we will factor that out. So the left-hand side becomes s squared plus 10s plus 24, that quantity times x of s equals this right-hand side. And so then we're going to, at the next step, solve for x of s by dividing both sides by s squared plus 10s plus 24. Now, one thing that we notice is that this quadratic factors into s plus 4 times s plus 6. So when we divide both sides of this equation by this polynomial, we get that x of s, this factor, over here still remaining on the left-hand side, is 1 over s plus 4 times s plus 6 times this stuff, which we have right here. Okay, now, next thing we notice is that in this parenthetical quantity, each of the two fractions has a denominator of s squared. So we'll factor that out, and we'll bring it all the way out to here. So x of s is 1 over s squared, s plus 4, s plus 6, times this exponential, which we have here, times 2s plus 1 times this exponential plus 1, which is what we have right here. Okay, and so the next step just does a little bit more algebra. This part here is unchanged, and so if we look at this part and use the distributive property, we can write minus 2s times this exponential as minus 2s times that exponential, minus 1 times that exponential gives us this term, minus 1 times that exponential plus 1. Okay, and then at the next stage, all we did was rearrange the terms a little bit. We still have the same stuff up here, and this term, minus 1 times this exponential, is right here, minus that exponential. This plus 1 was moved over to here. And we might wonder why we did that. Let's look ahead to see if we can figure out the rationale for making this change. Here we have a 1 minus e to the minus 2s, and right here we have another 1 minus e to the minus 2s. We're going to use that fact to simplify this expression for x of s. So far, we have that x of s is 1 over s squared, s plus 4, s plus 6, times 1 over 1 minus e to the minus 2s, times this stuff here. And then we can simplify it a little bit. Let's look at this 1 minus e to the minus 2s times this term plus this term, actually these two terms right here. If I look at, using the distributive law, 1 over 1 minus e to the minus 2s times minus 2s e to the minus 2s, that is right here. Minus 2s e to the minus 2s over 1 minus e to the minus 2s. Then we also have plus 1 minus e to the minus 2s divided by 1 minus e to the minus 2s, and that is equal to 1. Let's look at what we can do going from this step down to the next one. First of all, this fraction and this fraction are equal. And so what happened to this factor here? Well, we have the minus 2s and the e to the minus 2s right here. And we also have 1 over 1 minus e to the minus 2s. Let's remember that for small values of u, 1 over 1 minus u can be expanded as the sum where n goes from 0 to infinity of u to the n. So 1 over 1 minus e to the minus 2s can be written in that case as the sum n goes from 0 to infinity e to the minus 2 times n times s. That's the same thing as e to the minus 2s raised to the nth power. Okay, so this part should now be clear. What happened going from this step down to the next step? Well, we have an exponential times the sum of exponentials here. E to the minus 2s times e to the minus 2ns can be written as e to the minus the quantity 2n plus 2 times s. So that's the only simplification that was made here. These two factors combined into this one exponential factor. And of course, we still have the plus 1 out front. We still have the minus 2 s in here also. Now, what happened in going from here? What can we do at this stage? Well, let's see. We have this fraction times this term plus this fraction times 1. So the only thing that happened going from this step up here to down here was this fraction times 1 is equal to this fraction, 1 over s squared, s plus 4, s plus 6. Now, to get any further, we're going to need to use partial fractions, because we know how to, in many cases, find the inverse transformation of an exponential times a fairly simple fraction in s, a rational function of s. So let's expand expand minus 2s over s squared plus s plus 4 plus s plus 6. The details of this partial fraction decomposition are left to you. We've seen how to do it before. This fraction turns out to equal minus 1 over 6s plus s minus 1 over 6 times s plus 6 plus 1 over 4 times s plus 4 minus 1 over 12 times s, and then it's multiplied by this exponential. This fraction over here can also be expanded using partial fraction decomposition, and it turns out to be minus 1 over 72 s plus 6 plus 1 over 32 times s plus 4 minus 5 over 288 times s plus 1 over 24 times s squared. And so we now have x sub s written in this form. We're going to later take inverse Laplace transforms to get back to lowercase x sub t, the solution to our initial value problem. Finding inverse transforms of these four terms on the end is easy. This one's not hard either if we use the distributive property. Take this sum multiplied by this, as we'll see in the next slide. So we have seen that capital X of S is equal to this stuff times this sum minus these four terms. What we would like to do is to find the inverse Laplace transform of capital X sub S, which will be x of t, our solution to the initial value problem. So the first thing we'll do is to multiply this stuff out. So we'll start with this fraction, which is minus 1 over this stuff, times this sum, plus this fraction times this sum, minus this fraction times this sum. And so we can write that then as the sum of the inverse Laplace transform, and here is the term that corresponds to this fraction times e to the minus 2n plus 2. This term is this fraction times e to the minus 2n plus 2 times s, that is. This fraction here is just this fraction minus 1/12 s times e to the minus 2n plus 2s, and it's all summed from n equals 0 to infinity. Then x of t, as we just saw, is the inverse Laplace transform of this stuff, which we just got down here, plus the inverse Laplace transform of this stuff, which I just write as inverse Laplace transform of this stuff. Okay, so now let's look at this first term's inverse Laplace transform. We have a minus 1/6 out here, which can come out by linearity of the inverse transform. And then we have e to the minus 2n plus 2 times s divided by s plus 6. If we look at this fraction, we notice that it's of the form e to the minus as, since we have e to the minus 2n plus 2 times s, divided by s plus b, which in this case is s plus 6. And our inverse Laplace transform formula for that was e to the minus b times the quantity t minus a times that unit step function evaluated at t minus a. So the inverse Laplace transform of this term is just going to be that factor of minus 1/6 out front, and then e to the minus 6 times t minus the quantity 2n plus 2 times u of t minus the quantity 2n plus 2, u of this whole thing. And here we have e to the minus 6 times this whole thing here too. Of course we have that sum out front. The inverse Laplace transform of this second term in the sum is also by that same type of formula above, given by this. And then the inverse Laplace transform of this term, we have an s down here. If we look up here, it still falls in this category. If you just let b equals 0, you'll have 1 over s plus 0 here, which is 1 over s, which is what we have here. And so that one is also easy to find by that formula, and it is right here. Then we have the inverse Laplace transforms of these four terms. The first three terms are easy. We've seen formulas for those before, and so we'll just get 1 minus 172 e to the minus 6t plus 1 for this one, 1/32 e to the minus 4t. For this one, we'll have minus 5 over 288. Remember that the inverse Laplace transform of 1 over s is just 1, and so it's minus 5 over 288 times 1. And let's see, on this last one, the inverse Laplace transform of 1 over s squared is just t. And so the inverse of 1/24 s squared is 1/24 times t. So here we have a formula for the solution to our mass and spring problem. What is the extension of the spring from its equilibrium position at time t? So now we're going to use the software package SageMath to produce two plots. We'll look at these plots. One for f of t, which is the external force function, that periodic function with period 2, and also x of t, the solution to our initial value problem. So that will be the position of the mass at time t from the equilibrium position. Okay, looking at SageMath, the first cell, we first declare s, t, and n to be variables. We're going to assume that t is real. We're going to assume that s is real. And we're going to assume that n is an integer. Then we define our external force function. F of t equals t plus the sum of all this stuff, which depends on n, where n goes from 1 to 4. So let's look at this stuff. We have the quantity t minus 2n minus t minus 2 times n minus 1, that whole quantity, times the unit step function evaluated at t minus 2 times n. So we have t plus the sum of this stuff times, the sum of this factor right here times this factor right here, where n goes from 1 to 4. Then we're going to print f of t, and then we're going to plot that external force function f of t. We're going to plot f of t for t going from 0 to 8. The figure size is 4, that means it's fairly small. I don't want to draw a line, so line style equals nothing. I want to print little points in our graph, so marker equals a point. The marker size is going to be 1, and the number of points plotted, plot points, is going to be 1,000. I think I'm going to make one change here, and I'm going to let, in this plot, t go from 0 to 10. So let's run this cell, and it'll take just a little while. Okay, print f of t. Well, here's the value of f of t, the function f of t right here. T minus 2 times unit step function t minus 2, minus 2 times unit step function of t minus 4, minus 2 times the unit step function of t minus 6, minus 2 times unit step function of t minus 8. You'll notice that's a little bit different from what we have up here for f of t. Some simplification occurred before printing out the formula for f of t. Then we plot f of t, t going from 0 to 10, and here is the plot. This part of the graph starts at 0, 0 and goes up to 2, 2. So this is, I guess you could say, the graph of f of t equals t. This part here is f of t equals t minus 2. This part here is f of t equals t minus 4, and so on. So we can see that using our method of using unit step functions to define functions piecewise did work in this case. So now we are ready to plot the solution to the initial value problem x of t. So let's see what is going on in this cell over here. Okay. So u of t equals unit step of t. I issued this command because I would rather write u of t's than unit step of t. Just save some typing. N is going to be a variable. I'm going to assume that n is an integer because n is used for the sum that we're going to look at. So let's see. What happens next? We define x of t by x of t equals sum, and then we have a fairly long formula up here. Minus 1/6 times that exponential times a unit step function plus 1/4 times an exponential times a unit step function minus 1/12 u of this stuff, and that's summed where n goes, in this case, from 0 to 4. In our solution, n should go from 0 to infinity, but if I let n go from 0 to 4, that gives me enough terms involving these unit step functions just to show me what the graph looks like, basically between 0 and 10. And after that sum, as we see at the top of the slide, we also have some extra terms. Minus 1/72 times an exponential plus 1/32 times another exponential minus 5/288 plus 1/24 times t. So let's execute this cell. Let's run it. And so here is the x of t function. Let's remember that we were showing x of t. It's 1/12 times all of this stuff. And there's something that is not quite on the screen here. A factor of e to the minus 6t. I'm not sure where that appears here. Looks like the printing didn't quite line up correctly. I think that was maybe minus 3 times that. But in any case, maybe we should have printed it rather than show it. There seems to be a slight problem with the graphics here. So now let's plot x of t, t going from 0 to 10. And once again, I don't want the figure to be too big, so I have fig size equals 4. So let's run this cell. And here is a plot of our solution to that initial value problem. The mass starts at 0. At time t equals 0, the mass starts with displacement 0, and it also has velocity 0, and so this graph right at 0 is horizontal. And then as time goes on from 0 to 2, the mass goes up to a displacement of about 0.07, I guess, maybe not quite that much. And then it goes back down to maybe about 0.25. Then it goes up and down, up and down, up and down. So what's happening here is that spring system was over-damped, but we applied an external periodic force to it. And so that forced our system into this kind of periodic motion. So the solution does make sense. One thing to notice is that the force went from 0 to 2 several times. But down here in the plot, the oscillations only went to about 0.07. So these oscillations are fairly small. So what did we do in this lesson? Well, we expressed a periodic function in terms of unit step functions, a sum of terms that involved unit step functions. We found the Laplace transform of this periodic function by using the following fact. If a function f of t is defined on 0 to infinity and has period p, then its Laplace transform, capital F of s, is 1 over 1 minus e to the minus ps times the integral from 0 to p of e to the minus st f of t dt. Notice here that we're not integrating from 0 to infinity. We're just integrating over one period of this function little f. The integral goes from 0 to p. Then we needed to do some simplification so that we could find inverse Laplace transforms later. We looked at this factor in front of the integral, 1 over 1 minus e to the minus ps, and we used the fact that this looked something like 1 over 1 minus u, and 1 over 1 minus u would have an infinite series representation as the sum n goes from 0 to infinity of u to the n. So we just used that fact that you learned in calculus to write this fraction in this form. And then we substituted that into our initial value problem, and we then took Laplace transforms of both sides of the ordinary differential equation using the initial conditions also once we started taking the Laplace transform. And this gave us a power series solution to our initial value problem, which we were able to graph by using SageMath. It could also be graphed in other software such as Maple, Octave, MATLAB, and in fact virtually any software that allows you to plot could be used to plot our solution. In our particular case, we had an infinite series for our solution, but we used only a finite number of terms to get the solution out to a certain multiple of the number of periods that we were looking at. And so that turned out to be useful. We didn't have to evaluate the whole infinite series. So what is next for us to do? There will be a part called Lesson 17, Part 2. In this new part, will numerically approximate the solution to the initial value problem that we just looked at using MATLAB and a finite difference method. We will approximate derivatives in a discrete manner, and we will then use Octave to write and execute a computer program that will graph this approximate solution. The code that I'm going to write in Octave should also run in MATLAB. Those two programs are very close to each other in syntax and in how they run. So we will see that starting in Lesson 17, Part 2, some numerical methods. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.